So our targets here in lesson 5.4 are to be able to do the following things. We want to be able to multiply two radicals together, use the distributive property to multiply radical expressions, and then continue with rationalizing denominators, except now in our denominator we're going to have binomials. So we're going to have something in the denominator that has two pieces to it. So we're going to work through these examples first, where we're just going to multiply these two radicals together. So in example A, we want to multiply 2 root 3 by 3 root 5. So to do so, we're just going to take and rearrange the order here. We're going to multiply the numbers in front, the 2 and the 3 together, and then we're going to multiply the radicals together, the square root of 3 and the square root of 5. So when we do so, 2 times 3, of course, is 6, and then square root 3 times square root 5 is square root 15. Now we always want to check at this point to see if we can simplify that square root of 15 using the methods that we learned in lesson 5.3. In order to determine if it can be simplified, we have to think about our list of perfect squares. 2 squared, 3 squared, 4 squared, 5 squared, and so on. We can see that there is not a perfect square that divides into into root 15. Therefore, this cannot be simplified any further. Now, on the other hand, in example B, if we multiply the coefficients together, 3 times 5, and multiply the radicals together, square root 8 times square root 2, we're going to get 15 root 16. Well, obviously 16 is a perfect square, and its principal square root is 4. Therefore, this is equivalent to 15 times 4, which is 60. So that one could be simplified further. In example C, again, we're going to multiply the coefficients together, and then we're going to multiply the radicals. So 7 times 3 is 21, and square root 6 times square root 8 is square root 48. But again, we want to look to see if there is any perfect square that divides into 48, and there is. 48 is equal to 16 times 3, and 16 is a perfect square. So we're going to break apart this square root 48 into square root 16 times square root 3, and leave the 21 out in front. Well, this square root 16 is equivalent to 4. So now what we have is 21 times 4 times root 3. And 21 times 4 is 84. So our final answer is 84 root 3. In our last example here, we have cube roots. So again, we're going to start in the very same way. We're going to multiply the coefficients together and multiply the radicals together. So that'd be cube root 6 and cube root 4. And so the coefficients multiplied together, 2 times 5 equal 10, and the radicals multiplied together, 6 times 4 equals 24. But it's cube root 24, not square root 24. So now we have to think about our list of perfect cubes. 2 cubed, 3 cubed, 4 cubed, and so on. I can see that 8 divides into 24 3 times. So the cube root of 8 is equal to the cube root of, the cube root of 24 is equal to the cube root of 8 times the cube root of 3. And we'll just leave that 10 out in front. Well, again, now when you think about what number can you multiply by itself 3 times that is equal to 8, that's 2. Because 2 times 2 times 2, 3 times is equal to 8. So the cube root of 8 is 2. Nothing more can be done with the cube root of 3. So all I have to do is take that 2 and multiply it by the 10 that I had out in front by multiplying my coefficients. So my final answer ends up being 20 cube root 3.